This morning to have Rob Chandhok with us, who is President and CEO of Helium Systems, Inc., and will be our lead-off and a third keynote speaker as we begin this afternoon's sessions. Rob is now President and co-founder of Helium, which provides a complete Internet of Things platform for smart machines, and he will tell you more about that. Helium is a recent entrepreneurial adventure. Rob served as president of Qualcomm Interactive Platforms and was senior vice president of Qualcomm Technologies, where he was responsible for Qualcomm products and strategies related to software and the Internet of Things there, which include the All-Join and the All-Seen Alliance. He also led several wearable and VoIP projects. He's now the co-founder of Helium, as I said, which is developing scalable solutions that blend technology from advanced low-power radio and software distributed systems to provide an end-to-end solution. He's going to tell you more about that. And so would you please welcome from San Francisco, Rob Chandhok. Please. Thank you, Rob.
Thank you, everyone. I was just saying to George that this is the second time I've come to give a talk in Asia, and I'm the speaker right after lunch. So I'm not only happy that you came back from lunch to listen, but I'm hoping that less than 25% of you will fall asleep during the talk, as we've all had good food and we're warm and everything feels good. So a lot of the talks that you heard this morning were very focused on either a particular business or discussions of economies and markets, and I think that was actually really interesting, really fascinating. I will warn you that this talk is not one of those talks. There aren't a lot of numbers in my talk, but I want to try to get across and hopefully help tell you stories about the experiences that we've had trying to build technologies and ecosystems around what people are calling the Internet of Things. And I think it's important to think about this as an industry and as entrepreneurs, because in much the same way we talk about concepts like the sharing economy, and I feel like we all can get our heads around those kinds of concepts perhaps more easily because they're very personal to us. We can think about what would happen if I wanted to borrow my friend's car, but maybe I borrow somebody else's car and I didn't know them. What if there was a way to reduce that friction? Or in the Airbnb case, talk about sleeping in someone else's home and changing the dynamics of what you would normally do or share with friends, and bring that to happen also with people that you might not have firsthand knowledge of. But you bring up something like the Internet of Things, and it really is quite a different concept because it cuts across so many kinds of technology. So from the large to the small, the Internet of Things businesses cut across analytics, hardware, networking, new kinds of networking topologies, and so forth. And I'm going to try to talk through those topics. So the first thing I'd like to sort of put forth as a question maybe to you, is there such a thing as the Internet of Things? And it's a word that when I was at Qualcomm, we tried to, along with Cisco, use the word the Internet of Everything instead of the Internet of Things. Some people would say that M2M is actually what we used to call M2M is now what we call Internet of Things. There's an analyst report that I commented on Twitter yesterday that was trying to further declassify Internet of Everything into Internet of Humans and Internet of Things and Internet of I can't even remember the third term that they used because I didn't really understand it. To me, the Internet of Things is really things connected to the Internet. And what makes that different is these kind of things are not what we've been connecting to the Internet for so many of the past, going on 20 years. I mean, I've been on the Internet as it existed since the 80s. And most of what we think about when we think about connecting things to the Internet are devices, computers that have relatively large amounts of storage, relatively large amounts of compute, right, varying in various directions. But things seem really, really small. I mean, and I have some of them with me, some of the Helium hardware, and I can show that more. But something this size, which has a bunch of sensors in it and a radio and a little CPU, doesn't seem like the same thing as our smartphone. Well, when smartphones first came out, or before they were even called smartphones, we thought of that divide in the internet, and we said, well, we have the internet and we have the mobile web. And at the time, not only was the mobile web implemented differently on the phones in the early 2000s, but it was actually a different subset of the web, right? We couldn't run a browser at the time on those phones. Well, there are people in this room who did make that happen rather quickly. But at the time, we thought we needed different protocols like CHTML and a bunch of stuff that made the web smaller so it could run on smaller devices. And so we called that the mobile web. But we don't use that word anymore. We don't say the mobile web anymore because if anything, the internet lives on our smartphones. The majority of the transactions, the majority of the content, the majority of the creation. So we stopped using that term as those devices grew into and became part of the internet. So my prediction is that in 3 years, we won't be saying the Internet of Things anymore. We'll just be talking about the internet, but we'll be talking about a new set of devices. And if you think, but there are differences in things that are going to continue to cause us to think differently about them. So the transitions the internet have gone through are really ones of sort of scale in terms of classes of devices. And what I mean by that is, when we first started building the internet, it was a loosely, the name internet actually comes from, it was loosely connected protocols with sort of pockets of local connectivity. So the universities would have a network, and they would run one wire to another university or another wire to a government research institution. And it was very exciting because we didn't send mag tapes to each other. We sent, we could actually transfer files, and that was very exciting. But the number of machines was small enough that we could name them all in a file and say this address means this machine, right? And then the next explosion is we really started giving people access to it through broadband dial-up or even through modem dial-up, right? So you would have a single device in your house that would be connected to the internet, and that was all. And I can even remember when I keep talking about I can even remember like I'm really, really old. So I remember, Dave. He said a small number of devices. And I remember when ISPs actually tried to charge you extra if you connected a second computer to that line, right? Which is why all kinds of home routers developed to hide that from the ISP. And they realized that was a losing battle, and they just started doing that based on bandwidth. But for a long time, they tried to stop you from connecting that second computer, right? And then wireless came out, and then we got a whole other scale, because all of a sudden, not just one device per household, but one device, and in a lot of markets, multiple devices. But let's just even start with one device per person. So in that household that shared a computer before, all of a sudden there were 4 phones that were connected to the internet. So you got another explosion. And at this transition, and I was at Qualcomm in the 2000s, in that transition, we thought we were going to have to change the internet to make the mobile web work. And we had mobile IP, and all the network providers were going to say, we're going to fix the internet for mobility, and we're going to do things like keep your same address as you move around. Well, it turns out none of that stuff actually mattered in the end. When we were telling people how to write applications for the internet, and we would take people that had been writing desktop applications, the only thing they had to be able to handle that was different at the mobile web to really make it work was just know that sometimes your address will change, and just know that sometimes you won't be connected. And if you can write your application to handle that case, then it's pretty much the same as writing it on your PC. And then, lo and behold, 2007 rolls around. Apple puts out a very rich programming environment on the iPhone. Android follows very closely. And we get that explosion. But relative still to the Internet of Things explosion, it's small. Because now we're saying instead of adding that 4 per household, I might add 400 or 4,000 devices per household or per industry or per office or per factory. So the scale is quite different because we're talking about instrumenting things, we're talking about measuring things, we're talking about controlling things, and we're doing it all through the network. So a lot of what I've thought about in the Internet of Things over the last 6 years has been, what does that mean to the internet, not are we building a separate internet? All right, so think about that when you hear somebody say the Internet of Things. And if you want an interesting test to think about, when somebody says, I'm doing X for the Internet of Things, ask yourself the question, if they replaced Internet of Things with Internet, would it still make sense? So if somebody says, I'm doing security for the Internet of Things, can you replace that and say, I'm doing security for the internet? And if that doesn't make sense, because that doesn't make sense to say you're going to do all the security for the internet, right? It doesn't make any sense in the Internet of Things either. So maybe put that in the back of your head. Whoa. The other challenge of this is that I do some very, nice little orderly fractal things. But this is really what the Internet of Things looks like. It's not a pretty picture. The real world is a messy place, all right? And there's lots of connectivity that's different. There's ad hoc behaviors. We walk into the room. We may want to form an Internet of Things network just because we're at this conference together. I cannot describe that using the current tools of the Internet, right? We try to do that with geolocation, saying, well, if we're near each other in latitude and longitude, maybe we have something in common. But there might be people on the other side of this wall that also are very near to us in latitude and longitude that have nothing to do with this conference. So the kinds of systems that you build to do discovery, security, grouping, and so forth are different because the real world is a different place than the virtual world we've been living in. So that's another thing that I think is different when you talk about things connected to the Internet, is they have to be able to respond, interact, be named, and all kinds of other attributes because they have a place in the real world, and that actually is fundamentally different. Everything else we've tried to virtualize. What's great about WhatsApp is I can be talking to my kids now while I'm in Hong Kong, and there's no difference to them whether it's in Hong Kong, in San Francisco, in New York, in London, right? But if I want to interact with somebody or a thing or change the temperature in my room, changing the temperature in my room, most of the time, I want to do it in the room I'm in, right? Even though a lot of people think that's what's great about Nest is I can change the temperature. I guarantee that if I pulled my phone out and changed the temperature at my house, my wife would not be happy, all right? So the real world has different kinds of constraints. So let's think about maybe talking about how things can actually be sort of categorized in a little bit different way. So I've already talked about the fact that at least right now, relative to the rest of the things you're used to dealing with, they're resource constrained. And we all know about Moore's Law and how fast things are moving in that area. I won't be surprised that if we're going to have very, very small, very powerful SoCs and computing chips, I know where they're going, and it's happening very, very quickly. But as it is right now, it's still relatively resource constrained. I already talked about the fact that there's a lot of dynamic behavior. The fact that these things are in the physical world makes a difference, and it makes a difference in how we think about the connectivity. Now, we thought a lot, we've dealt with dynamic behavior when we added mobility to the Internet, right? I can now be connected to the Internet driving down the road at 70 miles an hour. That was hard to do before, and now it's straightforward to do. But now I'm talking about things also moving around at a scale we hadn't seen before without having as much compute and other capabilities with us, and at a very different price point too. So I can't afford to put the intelligence I put into a mobile phone into the 1,000 things that I'm going to sprinkle through my car, through my factories, and so forth, right? They're very distributed. They tend to be very distributed systems. If I'm doing command and control of something, whether it be the lighting system in my house, my entertainment system, or a factory line, or heavy machinery at a construction site, the information that I need to actually make that better is often distributed amongst what are now a bunch of little loosely coupled computers. Right? So it's a different kind of way of thinking about the system. A lot of people have done thinking about distributed computing in the large. How do I make big databases work? How do I make distributed computation work? And we have things like Hadoop, right? And MongoDB and Riak and a bunch of other really cool things going on the server side. How do you take those same concepts and bring them out to the small? And security also matters in this resource-constrained environment, right? And so you can't not think about it because now your attack surface, or the attack surface, your vulnerability surface is even greater. So you have to think about all these things, even though these things are small and everywhere, right? So the topology, the shape of this network, the shape of how you think about these systems, at least to the work that I've been involved in, leads you to a couple different design principles. One is that you get a lot of things that are more decentralized, right? If I have a lot of devices that are doing things relatively autonomously, right? I can't just take a design model. That's what I'm going to talk about in a good part of this talk, is what is the shape of how we compute, store data, and send data, and how might it change. I think there are going to be interesting opportunities for more local communication. So while you might be connected to the internet, it's a big capital I internet, when you need to be, you should be able to do things very locally here. Like we might be able to have a chat room completely without a server or share files just because we're in this same physical space together. And at some point, we might decide to share that with the rest of the world, right? Like I'm assuming that, I don't know if this is being live streamed, but it's being recorded, so at some point some of these videos will be up there. But where it is right now, it's an experience because it's physically here. Probabilistic, things about, this one's a little, I think, a harder idea to get across, but if you think about how a lot of these systems are going to really start to grow into something that is useful, is that we're going to start to use the same techniques that people use when they talk about machine learning and artificial intelligence, which is we're going to base our systems on statistics and probabilistic methods so that we can learn from information in the large that is distributed that we don't know a lot about, rather than thinking that we might actually be able to specify a rule for everything. All right? And if you think about it, it's the difference between trying to build a recipe for every behavior or thing that you want to do when you walk in and out of your house, all right, or having a system that notices that, oh, usually you come home, you turn on the hall light, you set the temperature to this. People are starting to nibble at the edges of that problem in the consumer space, but it's what we've been doing all along on the commercial side. I mean, it's what we do to learn about advertising. Nobody writes an ad system right now, or the financial system that was spoken about just a minute ago in the last panel. You wouldn't sit down and try to do your risk management system by writing a set of rules that says, if they write in capital letters, then do this, because it blows up combinatorically, right? Like, I don't know, for example, how if this then that is going to turn into a system that I can use, because I've tried to build rule-based systems before, and after about 5 rules, I can't keep track of it anymore. So it works for really simple tasks, but it doesn't work for what we expect now. What Google now gives you, or what Siri gives you, is based on these kinds of statistical probabilistic machine learning algorithms, not a bunch of rules. And a lot of people are thinking about Internet of Things, think they're going to be these very simple rule sets, and that I don't think will be the case. Self-configuring. With a lot of things, in order to get to the scale with consumers and businesses, I think we're going to have to build systems that work right out of the box. You turn them on, they see what's around them, they connect to the things they need to connect to, and they start doing their job. One of the examples I'll give there is the guy that did the Roomba, the first robot vacuum cleaner. And sorry, I don't remember his name. That must be the jet lag or my age. I can't tell which. He has a new company that's doing a different kind of robotics. They're doing a robot called Baxter. I do remember the name of the robot, though, for some reason. That is trained by a human picking up the arm of the robot and teaching them to do a task. All right? But the thing that's self-configuring about that is that the robot has to be physically aware of its surroundings, because if it calculates wrong and hits the person that's standing next to them, it could do quite a lot of injury. So that robot has to understand its environment and sense it in order to be able to be that much more configuring. As a result, or their business goal is to build a robot system that can either help or replace sort of repetitive tasks on the assembly line without having to have a large-scale system integrator sit down and program the robot for 2 weeks to get that motion exactly right so that it doesn't cause harm and so that the factory works. All right? So that self-configuring behavior is what we're going to start to see, I think, on the things side as well. And the other thing about the topology is going to be secure. We don't have great systems for this. At Helium, and I'll talk about it a little bit, we believe really strongly in security, and we've taken a certain hardware-based approach. But you're going to see that theme over and over again as people try to think about, how do I secure something when I don't know at the beginning who owns it? I don't have a large corporation that's managing it, right? One of the things is, like, think about what would be the equivalent of a SIM card for the next trillion devices, right? Because this isn't going to be a SIM card. It's going to be something else. All right. So I'm going to talk a little bit about some design patterns. So a lot of what we are used to, and a lot of what we think about, and a lot of what people think about as big data, is what I sometimes think of as computing at the core, right? So we've got a lot of designs out there where, even in the Internet of Things, what the design pattern is that you take some data from all these nodes, and you, as fast as you can, get it back to the cloud. And in that cloud, you have this magical big system that actually reasons about it, and good things happen. And it's a good design pattern. But think about some of the things that I was saying before about the physical world as a messy place. Sometimes in this world of physical things, going back to the cloud and coming back takes too long, right? So we're not used to, as we think about, well, who's going to be the next WhatsApp, or what's Facebook going to do next, or what's Twitter going to do, or Airbnb, or anybody. We don't think about that latency because in the time frame of those systems, it doesn't matter if it takes 100 milliseconds or 600 milliseconds. But in the physical world, that can be an eternity. If you're controlling a machine, a robot arm, a motor, something like that, microseconds could matter. Now, I'm not saying everything's microseconds, but you have to think about that. We've built a system that has basically gone back to the client-server model of the 80s, right? When we have these debates in computer science all the time and we swing pendulums back and forth between saying all the compute will be at the edge, all the compute will be in the core. And a lot of the great business and commerce that's happened in the last 10 years have been by exploiting the compute in the core because we've had really fast connections for a lot of things that have to do, that aren't as time sensitive. But the Internet of Things has relationships with the physical world that are time sensitive, right? If I can't control my car, could you imagine if you're trying to do a car control system and it depended on the compute happening in the cloud? I would never get in that car, right? I might want to be advised by that car, but I don't want my brakes controlled by something that has an intermittent wireless connection. And I worked at a company that makes great wireless connections, but they don't work 100% of the time, right? Because that's the physical world, right? So you have to think about a new pattern. And that new pattern is a little bit of compute at the edge. And that's not saying that we don't compute in the core. And saying that you push what you're thinking about out to the edge of the network, right? And you push intelligence. And remember we talked about a little bit ago that even though right now these devices are less capable, they're getting more and more capable. I'm starting to talk to companies now that believe that we can push some really beginnings of machine learning algorithms out to very, very tiny devices at the edge. So imagine systems where you talk to the central cloud every now and then and get advice, but then you run these algorithms at the edge, and you can share the learning. So maybe I want to share the learning between these two nodes, but that kind of learning, I only need to share that maybe once a day or twice a day. I'm making that number up, right? But I might need to use that learning every 10 milliseconds, right? So it's very expensive for me, first of all, in a lot of situations, to send that data back and forth. But even assuming expense wasn't the problem, it just isn't fast enough a lot of the time. So I think one of the features of the Internet of Things is going to be that we're going to push more intelligence out to the edge of the network. Now, I have a data point for that I think a lot of people don't think about when you think, I don't have my phone, I left it in a chair, but if you think about your phone, you think about that as very connected to the internet, right? You think about the way that you get your data. If you're, I had friends that when they first got their children iPads or a tablet, and they were Wi-Fi only, they would get into the car and the kid would be driving down the road and the kid would say, the tablet's broken. It doesn't work anymore, because they just expect 100% connectivity. But without the connectivity, a lot of the things that you do don't work. Your email doesn't work, your Twitter doesn't work. So it's great to have that cellular data connection. But you can't always depend on it. So one of the things you don't realize, though, about your phone is that even though it's connected like that all the time and you get that great experience, there are parts of it that have been pushed to the edge already, right? And one of them is the user experience, the user interface. For those of you that remember when Android first started relative to the iPhone, it used to have really relatively poor sort of feel to it as you scrolled around and moved around. It's because they were doing all the compute in the CPU. So at some point, they started to render their UI using the graphics processing unit, which most people think is just there for games. Mostly what that GPU is used on a phone is actually for user experience and user interface. So when you scroll your finger down, right, that's why it's so smooth, right? So when it feels like butter, like the name of that project was to make Android better, it's because it's using local computing resources to do things because the latency involved doesn't work. You would never say, oh, the user said scroll down, send that to a cloud, tell me what to draw next and come back down. It just doesn't work. That's what's going to be multiplied by 1,000,000 times when you start to the Internet of Things. You just won't see it because things don't have displays, things don't have speakers most of the time, things don't have anything but other kinds of invisible connections to the real world. So think of that as a design pattern that might change. All right. I'm going to talk very briefly, because I don't want to do a commercial for Helium, about what Helium does and tell you give you some examples of how we're using those design patterns and we're thinking about the problem a little bit differently. So Helium started as thinking about how to make things easier to connect to the internet in general. And we started out building radio systems called an atom, right here. And we connected that to our own kind of access point, and we made sort of a system that made it easier to get data onto the internet, but it really didn't say anything about the data. So we have a little module. For those of you that love hardware, we have this little tiny thing that you can put into anything else, and used unlicensed band, actually, for the nerds out there, 802.15.4 physical layer with our own MAC layer. But the idea being it's make it easier to get things onto the internet. And we realized that wasn't really solving enough of the problem. So what we're providing now in our platform, what our current business plan is, and as sort of the entrepreneurial message in this is, if you're also going to go out and leave that big company, as was previously advised, quit your jobs and go start a new company, don't be afraid to pivot either, right? Because you think about what you're doing, you think you know the market, but you learn things every day that's going to teach you about where you're going to go next, right? So that's the other thing that I would say. The part of being uncomfortable is not having a 3-year business plan, or knowing that the 3-year business plan you wrote yesterday might change tomorrow, right? So there's the lesson there. And Helium, when Vinod Khosla was recruiting me to Helium, one of the things he said to me is, look, I don't know Internet of Things exactly where it's going to go, but it's a big space and it's a fantastic team. And so we'll figure it out. So one of the things that we're doing is we're thinking about how to take an end-to-end system where we have sensing, where the sensors can actually get more smart over time, more intelligent over time. And we're tying that to sort of a classic large-scale distributed back-end cloud that has all the things that you think about. It can do analytics. It can host different compute things, but I think most differently about it is we're trying to really think about that problem of computing at the edge. And one of the problems right now is a lot of the computing at the edge happens by first you get a bunch of people that write really cool stuff in the cloud, and they get to use all kinds of great tools like the Elastic Compute Web or tools with Google or something like that, and you get the server side of that up really, really quickly. And then you have this part of the system, and this is EE's programming in assembler in C using tool chains that haven't changed for the last 20 years. And there's a mismatch between the design cycle you can have on the cloud side and the design cycle you can have on the thing side, right? So one of the things that we're doing at Helium is we're thinking about how can I make it easier to program things of this size by making them part of a full system. And there are other folks that are doing things that are a little bit similar to making this easier. ARM has a really cool initiative called Embed. There are a couple other people that are thinking of the problem. There's some new operating systems that are really, really small coming out. But the end-to-end problem is, what I want to be able to say is, I want to be able to change the behavior of this thing at the edge, but I want to manage it the way I manage the rest of my business. And the rest of my business I manage from the cloud, right? So Helium is about bringing the efficiencies, the scale, and the speed of the cloud out to the edge of the network. And we're going to do that with sensors, and then we're going to do that in some other application domains. So that's the end of my commercial, and I'll give you some examples. So if you think about, there's a pointer. If you think about the parts of our system, so here's a sensor. This is supposed to be the access point, which may have some computing power in it. Our cloud server, and then other parts of the system connect to the internet. So our customers might want to use something there. So there may be times in your system where you don't need any availability or any connectivity past a little bit past the access point. But nobody really builds a system like that. Usually, the only thing you do is the pattern that's on the bottom, where you go out, talk to your server all the way back, and round trip the data back. So we're thinking about systems that can accommodate different levels of connectivity by pushing compute out to the edge. And I'll try to give a couple more examples of that. So one of the ways you can think about the the way you might think about Keynote is in the past, you sort of, when you're building a system, and I'm using the Helium components in here, but you'll see this, if you think of that side is more towards the cloud, this side is more towards the edge. You don't have to know the difference between an atom and an element. We had teams, when we built systems like this, we had teams that worked on each of these different areas. So you would have the firmware guys working over here, and you might have a little bit of apps programmer, and then you had the people who did the server backend, and the people who did the user experience. And there's a lot of work spread out over all of these things. So that's sort of a classic, let's build a product kind of thing, right? That's been a design pattern. Big data kind of shifted that stuff around a little bit. A lot of what happened in big data is we sort of took away from what we were doing here, and we spent a lot of time reasoning about the data that we were getting, but we did all this reasoning on this side of the world, in the cloud and in the large, all right? And I'm not saying, by the way, I am not saying at all that that's a bad design pattern. I'm just saying it is a design pattern that may or may not work for everything in the world. Although we've almost convinced ourselves at this point in time that if I can just shove a lot of data up into the cloud, big data, this mysterious thing called big data, means that I can then make a business out of it, right? And that's no more true than any other sort of easy answer to any problem. But that's a design pattern that I think the internet infrastructure as it is right now does very, very well, and that's why companies can move so fast, right? If you want to stand up a system that uses this kind of a design pattern, there's hundreds of tools and building blocks and open source projects and companies that will host your stuff for you. If I want my website to go faster, I go to Cloudflare, right? And I get a piece of the puzzle from them. If I want to do my analytics faster, there's 5 companies now that I can go buy analytics for. I even think in 2 or 3 years, we're going to buy machine learning access and access to machine learning algorithms, just sort of like the same way we buy disk space right now. Because they're getting to be classes of problems, not to make a pun, but like certain classification problems and so forth, that you can actually generalize enough. We're almost getting to the place where we can host those as services, and there are companies that are playing around with that, right? But that solves this kind of a problem, right? But it doesn't help me solve the problem when I want to actually spread that out to the edge and now be controlling or interfacing with those next billion or trillion devices. So this is the sort of the controversial side possibly, or this is the thing that Helium itself is trying to exploit. We're trying to think about what we call big data in the small. So there's a lot of data being generated, but because of the kind of data that it is and the latency constraints that you might have, you may want to actually do a bunch of the algorithms over here. So what is the combination, or some people would call it the partitioning of the system, that allows me to do things that learn and take advantage of big data, but yet run on 100,000 small devices instead of on 5 really big ones, all right? And so we're looking at what kinds of programming languages we'd use for that. How would you describe those systems? What if I want to do is, over time, get smarter and smarter, but I'm willing to take a certain amount of time to learn that because I get a scale that I don't get any other way. So those are sort of hard problems to think about, but I think it's a design pattern that's not going to go away in the scheme of things. So if I could ask you to think about something after this talk and walk away and think about it, is when you hear somebody say the Internet of Things, think about the different kinds of things that they might be talking about, and also consider that doing the next thing might involve thinking about how you do the compute a different way than you do now. Because I think if you do that, especially those of you that are thinking about starting companies, I think there's a lot of seams here to exploit. There's a lot of new frontiers that nobody is doing really, really well. And I think there's a lot of opportunity. So what you might end up with as you build these, and we have a really good graphics designer, so I get to put up really science fiction pictures when I do that. But imagine systems that look at hundreds of thousands of sensors and the data coming from hundreds of thousands of sensors, make inferences about that, draw connections. And you could argue to me, Rob, that's the same thing as just all the big data stuff that we're talking about, right? I'm doing correlations. I'm doing all the stuff that all the big data companies are doing. But then pushes this knowledge out to the edge of the network to the point where those things become more intelligent over time. That's when I think you get the scale that we're talking about. So with that, I'm going to return some time back to the conference, and thank you for listening.
Thank you, Bob.